Good evening, ladies and gentlemen. How are we all tonight? Good. My name is Mark Razzi. I'm from the Public Services Office here at the lab. Just wanted to thank you all for coming tonight. All of you on the net, thank you for joining us as well. Jupiter's moon Europa may be a habitable world. There's evidence that suggests there may be a global subsurface ocean beneath the moon's icy shell, and the lack of large craters suggests a surface age of only 60 million years, implying that Europa is still geologically active. Tidal flexing of the floating ice shell generates stresses that can fracture and deform the surface to create Europa's intriguing troughs, ridges, and bands. And it is this unique moon's astonishing geology and astrobiological potential that make it a top priority for space exploration. Tonight's speaker received his BA in Geological Sciences from Cornell University in 1986, then went on to obtain his PhD in Geology from Arizona State University in 1994. From 1995 through 2001, he studied at Brown University as a postdoctoral research associate in geological sciences. Then, he became an affiliate member of the Galileo imaging team and worked to plan many of the spacecraft's observations of Jupiter's icy Galilean satellites. Then, in 2001, he went on to work as an assistant professor of planetary sciences at the University of Colorado at Boulder until 2006. Today, he is a principal scientist and director's fellow in the Planetary Ices Group within the Sciences Division of the Jet Propulsion Laboratory here in Pasadena, California. His research focuses on the processes that have shaped the icy satellites of the outer solar system, in particular Europa, and the role of its probable subsurface ocean. Such research includes the possibility that convection has played an important role in the satellite's history, investigation of regions of separation and spreading of the satellite's icy lithosphere, and the existence of a liquid water ocean beneath the icy surface. And while busy with all this, he continues to publish scientific research papers, serve on a variety of teams and committees, mentor graduate student researchers, and work with various museums and organizations to bring the excitement of astronomy and planetary exploration to the public. Ladies and gentlemen, please join me in welcoming tonight's speaker, Dr. Robert Pappalardo.
Thank you, Mark. You've heard it all. It's a pleasure to be here, and thank you all for coming. It's a great crowd tonight. I have the pleasure to be able to introduce to you this fellow here, Europa, one of the moons of Jupiter, and arguably one of the most fascinating bodies in our solar system. Not only because we don't really understand what's going on to make this cracked eggshell-like appearance on this moon, but because we think we understand that beneath the icy shell of Europa lies a global subsurface ocean, more water than the volume of all of Earth's oceans combined. So what I'd like to do this evening is bring you on a tour of Europa through the various kinds of geological features we see on the surface and what we think they tell us about what's going on beneath the ice. So our story has a couple of heroes. Bring you back to 1610 and the first pictures, if you like to call them that, of Europa and the other moons of Jupiter. It was in 1610 that Galileo first pointed his spyglass toward the heavens and realized there was something strange going on around Jupiter. On January 7th, 1610, he made this sketch of Jupiter and these little stars as he thought they were. And then on the next night, they looked like this. And on the next night, it was cloudy in Padua. And then on subsequent nights, he realized these little things he thought were stars were going around Jupiter. They were somehow related to Jupiter. Now we know they're moons, Io, Europa, Ganymede, and Callisto. And we can go to the solar system simulator page at JPL and punch in those dates and the view from Padua, Italy at about 7:30 in the evening and understand what he was seeing, exactly which of the moons he was seeing, which nights have labeled which of the moons here. In the first night, actually, Io and Europa were right on top of one another. He thought it was one. He saw Io, Europa, and Ganymede on that second night and missed out on Callisto. So why was this so important? Because about 50 years earlier, Copernicus, in his book, essentially published on his deathbed, said, oh, hypothetically, perhaps the sun might be the center of the universe rather than the Earth. Perhaps the planets were going around it, and perhaps our moon was going around the Earth, and the rest of the planets going around the sun. And so there were multiple centers of motion in this idea, rather than the Earth being the only center of motion and everything going around the Earth. He hypothesized that there were multiple centers of motion. And what Galileo's observations did is prove that Jupiter was a center of motion. So if Jupiter was a center of motion, maybe Earth was, and the sun was. And so indeed, maybe the planets were going around the sun and our moon going around the Earth. Now, one of the other heroes of our story is also Galileo, but this Galileo, and the one where you can see the model in the next room, I invite you after the talk, if you didn't see it beforehand, see the life-size model of Galileo in the next room, and its tape recorder and its broken antenna. And it, from 95 to 2003, orbited around Jupiter. And with each orbit, it would make a close flyby of one of the large satellites, Io, Europa, Ganymede, and Callisto. Now, Io is the most volcanically active body in the solar system. And Galileo, the spacecraft, saw active volcanoes and active volcanism. That volcanism had been discovered by Voyager, of course, some years before that. But Voyager was just a flyby, flew through the system. There were two of them, one after the other, and got snapshots. But Galileo, with orbiting around Jupiter, was able to revisit these moons time and time again. So Io is a rocky world, volcanically active. Ganymede and Callisto are kind of part rocky and part icy, about half and half. Ganymede has parts of its surface that have been torn apart by tectonics. Callisto is kind of a boring, dead, cratered ice ball. Europa is actually mostly a rocky object. We know that from its density. We know its mass from its orbit. We know its size, so we know its volume, so we know its density. So we know its density is kind of like the density of rock. But from telescopes, we know that its surface is icy. We can look at the spectral fingerprint of reflected light off of it, so we know it has an icy surface. So what's going on is it probably has a skin of H2O above a rocky interior. So it's an odd moon. Here's what the surface looks like closer up. It looks different from, say, our moon or, say, Callisto, because it isn't covered with craters. There are very few craters. Here's one. Its name is Pwyll, or Pwch if you're Welsh. Here's another impact structure of some kind, but there are really very few. In fact, from the number of big craters on the surface, only a dozen or 20 or so, we can estimate how old that surface is, how long it's been since that surface was repaved. And that's only about 50 million years. It sounds like a long time, but on geological time scale, that's the blink of an eye. It's 1% of solar system history. What's gone on for the other 99% at Europa, we're not sure. So strange place, young surface, crisscrossed by these ridges and bands. Then it has this other mottled looking terrain. So what the heck's going on there? Well, again, from the density of Europa, we know something about what's going on inside. And better than that, from gravity, from the Galileo spacecraft going by Europa, making close passes by Europa, we have an idea not just of its density, but the distribution of mass inside. Essentially, by feeling out the gravitational field as the spacecraft goes by a planet or satellite, we can get an idea of how centrally concentrated the mass inside is. So we know Europa probably has an iron core down there in the center, and then its rocky mantle, and then again this skin of H2O, about 100 kilometers worth, plus or minus. How much of that is water remains an important question. Why do we care, really? I mean, if it's ice or water, well, because at least everywhere on Earth where there is water, there is life. Of course, an important goal for NASA, an important interest of the public is there life out there? Are we alone? Is life common? We're not talking about fish and whales, but we're talking about microscopic life, microscopic organisms. Could they exist within Europa? That's a lot of the driver to understand what Europa might be like beneath its ice. So we know it has a skin of H2O, but from the gravity data, we don't know if there's liquid there. I'm going to argue in a little bit that from the geology, we think there's liquid there. But the geologists, such as myself, are kind of scooped by the folks who study magnetic fields of all things. Because it turns out Europa and a couple of the other moons of Jupiter, Ganymede and Callisto, are acting like conductors. So what's that story? Europa is orbiting within the gigantic magnetic field of Jupiter. If you could see the magnetic influence of Jupiter in the sky, it would be about as big as seen from Earth as the full moon is. That's the magnetic influence, the magnetic field of Jupiter. So here are the satellites. Here's Io, here's Europa. They're minding their own business, trying to orbit around Jupiter, and they're immersed in this immense magnetic field. Jupiter's acting like a giant magnet. When the Galileo spacecraft made its flybys of Europa, it was realized that there was something going on near Europa, some sort of local magnetic field. And at first it was thought, well, maybe Europa has its own magnetic field. But strangely, that magnetic field is in the plane of the equator of Jupiter, in the orbital plane of the satellites, in the plane of Europa's equator. That's a little odd, but not unheard of, okay. But then another time when the Galileo spacecraft flew by Europa, the magnetic field had reversed. North had become south and south had become north. Well, that seems pretty weird. So what's going on? What's going on is that here's Europa minding its own business, orbiting around Jupiter. We're looking at Jupiter and a representation of the magnetic field lines coming out of Jupiter. This is a representation of the Io torus. Io is kind of a litter bug, and its volcanoes spew dust and gas, which forms a donut-shaped region around Jupiter. So that's kind of marking the influence of Io. Well, this magnetic field of Jupiter is tilted by 10 degrees, okay? And this torus is tilted with it. So sometimes Europa and the other satellites find themselves above the magnetic equator, if you like, of Jupiter. So the magnetic field kind of has an equator like this, but the satellites are orbiting in the real equator of the planet. But the magnetic field has its own equator, and that's tilted. And Jupiter is rotating pretty quickly, once in 10 hours. So here's this tilted magnetic field. It's rotating with Jupiter every 10 hours. And being tilted, it kind of flops around. So this is what it would look like half in orbit later, that tilted magnetic field. And look where Europa is. Now it's below this magnetic equator. So Europa and the other satellites are feeling a magnetic field from Jupiter that alternately points outward when it's above the magnetic equator, and then inward when the satellite is below the magnetic equator. And the satellite hasn't done much except orbit a tiny bit around, but Jupiter is rotating around and its magnetic field with it every 10 hours. So about half that time, the satellite is feeling a magnetic field opposite that it just felt a little while ago. And what the team studying the magnetometer data from Galileo found is that magnetic field of Europa was flipping to compensate, to oppose the magnetic field of Jupiter. So Europa's magnetic field would be pointing this way, and then it would point that way to oppose the magnetic field of Jupiter. So the bottom line, what this story is all about, is that to do that, Europa had to be behaving as a conductor, conducting electricity, essentially. Well, what can behave as a conductor within an icy moon? It had to be shallow, the magnetometry folks said, except salty water. Salty water conducts electricity very well. It's either that or Europa's made of copper, which it's not. Sure, it has an iron core, but that was too deep. So that's really the discovery of the ocean, comes from this magnetometer data. And then strangely, that was found at Callisto, which is kind of a dead world, and at Ganymede as well. Ganymede has its own magnetic field, but it has one of these induced magnetic fields as well. So oceans, it turns out, seem to be common within big satellites, but we'll talk later about why Europa's is really pretty special. So there seems to be an ocean at some depth below the ice here. And as a geologist, I want to understand how deep that ocean is. Does it communicate with the surface? That is, does it leak onto the surface through fractures or something? Is there a way of exploring? Can we get through this ice someday if we land something on Europa? Or are there other indirect ways that we can understand how deep that ocean is, what it's like, and is it a habitable place? Could microbes get by there and be happy there? Is it a place where we might be able to search for life? So here's what Europa looks like if you unwrap it into a map. And say we talk about these lines, these linear features. Well, what could they tell us about, well, not just the history of Europa, but about whether there could be an ocean beneath? Well, geologists like to map things. So the first thing you do is map these. Whoops. Oh, that wasn't what I thought it was going to be. That's okay. Let me zoom in on these features first. So we were able to get some super high resolution pictures with the Galileo spacecraft of what this kind of terrain looks like. And it kind of looks like this. It kind of looks like a bowl of spaghetti or something, with ridges crisscrossing one on top of another. So these things are ridges, but not just one. They kind of travel in pairs across the surface. What the heck's that about? This doesn't look like any other moon that we've seen anywhere else. What about these spots on the surface of Europa? Here's a zoom in on one of those. It's as if something dark kind of flowed out and covered up those ridges. Here are some of those ridges, and they look like they've almost been melted away, or somehow, this looks like a sizzling hamburger to me a little bit. So something strange has come along and almost cooked Europa's surface. So when we look at these ridged plains, we want to map out these lines, these linear features, try to understand how they formed, try to understand their patterns, what they look like, how they crisscross one another. There's a lot of information in there. Some of them, look at this guy. I mean, that's pretty weird. You don't see that anywhere else in the solar system. What the heck is doing that? So here's the map I thought I was going to show earlier. Here we go. So we can map out these global features on Europa's surface and then try to understand the stresses that form them. So how was the ice deformed, stretched, in order to form these features? Because they sure seem like they're cracks, and when we look at them close up, we can see that they've opened up, essentially. Well, the red areas here are predictions where the stresses should be pulling the surface apart, tension, and the blue lines are areas where the surface would be pushed together, compression, and a map of these linear features. And if the linear features are perpendicular to the red tick marks, then it's kind of a good fit. That is, then the tension could have pulled apart a fracture like this. So it's a decent fit to this stress pattern. So we come up with ideas for how the surface might have been ripped apart, and then try to compare them to what we see and see how good the fit is. Well, what is this stress field that seems to be a decent fit to Europa's features? It's the stress field if Europa's ice shell is rotating relative to the interior, slipping relative to the interior. So this is a weird idea, and people thought, well, let's just try that. Maybe that'll fit. And it does. So what this tells us is that the ice shell isn't firmly attached if you like, firmly joined to what's underneath. It seems to somehow be lubricated by something underneath and very slowly pulled relative to the interior of the satellite. So most moons always face their parent planet, and our moon does this. And so if that's the sun, if that's the Earth and I'm the moon be going around and always facing the same face toward the Earth. But Europa's ice shell seems to be not quite synchronous, but slowly slipping like this. So that's a piece of evidence for an ocean within Europa. Now there are more stresses that might break the surface, and they too relate to an ocean probably being beneath. This looks like a complicated diagram, but I'll show you the basics of it. This is an exaggerated view of Europa orbiting around Jupiter, looking down from over the North Pole. And Europa is in an eccentric orbit, an egg-shaped orbit, an oval orbit. So it's sometimes closer and sometimes farther from Jupiter. Again, this is way exaggerated so that you can see what's going on. And when Europa is closer, it's stretched out more by Jupiter's gigantic gravity. And when it's farther away, well, it contracts a bit. It's not stretched out nearly so much. So as Europa is going around, it's getting stretched outward and then released somewhat, relaxed somewhat. At the same time, it kind of nods back and forth, facing actually kind of in this direction, kind of in this direction as it orbits around. For the astronomers, for the JPLers in the crowd, this is libration. It's moving back and forth, and that's because it's in an orbit that's not quite circular. So it's nodding, and it's being pulled back and forth. It's stretching. And if you were to bend a paperclip back and forth for a while, you'd see that it gets hot. There's friction. And when something's bending back and forth, that friction generates heat. So what's going on, because Europa is squeezed in this way, is it's heating up inside. Now, we don't really know where this heat is. It might be in the mantle, like this is illustrating, or that heat might all be generated in the ice shell itself. This is called tidal heating. You might have heard of it, especially in the context of Io. That's why Io is the most volcanically active body in the solar system. And Io too has one of these eccentric orbits. In fact, the orbits of Io and Europa are tied together. It's because of Io and Ganymede, Europa's neighbors, that Europa has its eccentric orbit. They're in this orbital dance together. And actually, Callisto's not in that orbital dance, which is why it's kind of a boring moon, at least as we think. So Europa, there's a reason to think that Europa's interior could be hot, could be warm enough to melt liquid water if you go not too far down below the surface, even though the surface itself should be something like minus 350 degrees Fahrenheit. Oh, is that right? Yeah. About 100 degrees Kelvin. So this orbiting around Europa, sorry, I'm having a slide issue here. Let's see if we can fix that. Whoa, close enough. This orbiting around Jupiter creates stresses too. So getting stretched out, Europa getting stretched out when it's close to Jupiter, pulls apart the part of the surface that's facing toward and away from Jupiter. So there's tension in this area and in this area, and it pushes together the other areas. But that's just in one place in the orbit, when it's closest to Jupiter. It's orbiting around. And this is happening pretty quick. Europa goes around every 3.5 days. Every 85 hours, it makes an orbit. So these stresses must be changing as Europa orbits. And this is an animation of how the stresses change while Europa orbits around Jupiter. So if you're standing here on the surface, you go through tension, and then compression, and then tension again as Europa's orbiting. So this surface is just getting squeezed and pulled and pushed together just in the time scale of Europa's day, 3.5 Earth days, 85 hours. If you're over here on the surface, the stresses are not just changing from compression to tension, but they're rotating around. If you can see that in the back, these little tick marks are actually rotating around. So what would happen if a fracture formed and tried to, and was getting pulled apart by these stresses as it formed, as it moved across Europa's surface? Well, this is what we think would happen. It would make one of these strange arcuate features that we saw earlier. These things are called cycloids or cycloidal ridges. They were first seen in Voyager images. They weren't seen great then. They were seen at a couple of kilometers per pixel. And they stayed mysterious for 20 years until the Galileo spacecraft took more pictures of them, but more important, until smart people thought about how they might form and how they might relate to these changing stresses on Europa. So it was Greg Hoppe and Randy Tufts at the University of Arizona who realized the stresses change direction as Europa orbits around. And they put together this little animation. If you're a fracture and you're trying to follow that changing stress direction, you can trace out an arc across the surface. And when the surface goes into compression, you just sit there and that fracture kind of rests, waiting for the next Europan day, making an arc each Europan day. So again, this is fascinating geologically, but what's the big picture? Why do we care? Because these stresses related to the flexing of Europa as it orbits seem to have made geology, seem to have cracked the surface of Europa. If Europa has an ocean, then those stresses can be large. The tides on Europa can be large, about 30 meters or so, 30 yards. But if Europa has no ocean and its ice shell is clamped right to the rocky core, then the tide is only about 1 meter, about a yard, 3 feet. So the fact that we see features that seem to be related to the tides have cracked Europa's shell, tell us that there's probably an ocean down there. Without an ocean, those tides just wouldn't be large enough to do anything to the surface. So Europa's ocean was kind of staring us in the face, evidence of it, for 20 years, but we didn't know how to interpret it. We didn't understand that information. Now, we don't know from just these features alone that Europa's ocean is there today, except the magnetometer data says, yeah, it's probably there today, because we don't know how old these are. But then again, the crater data says these are probably formed in the last 50 million years. That ocean probably is there today. So what do these ridges look like close up, or any of Europa's ridges? We saw a little bit of that before. These double ridges, whoops, my computer is having issues there. There we go. These double ridges that stretch across the surface. Galileo was able to take not just regional views, but close-up views. And here we're zooming into one of those mosaics of images from Galileo, colorized by some lower resolution data, to see what these ridges look like close up. Again, it's amazing. There are these valleys inside a ridge, or two ridges side by side, or however you might describe this. They're big boulders that seem to have rolled off this thing. This is about 2 kilometers wide. What's that, 1.5 miles or so wide. Some of these go for 1,000 kilometers across the surface of Europa. Scientists are still arguing today how these things formed. We don't really understand it, but we have some good ideas that are still being debated. Here's a set of models of possible ways these ridges might have formed. Maybe some stuff spewed up from the ocean along fractures, or maybe the squeezing from the tides squeezes stuff up to the surface, or maybe there's compression. Well, the model I believe most is the one in the big one up in the center there, that says that what happened is that Europa's surface cracks from these tides that we talked about, and once it's cracked, then these stresses that are rotating around and changing during the day can cause each side of the fracture to move back and forth during the course of Europa's orbit, during the course of Europa's day. And like rubbing your hands together, if you do this for a while, your hands get warm. It doesn't take too long before your hands get warm. And in the same way, if Europa's ice plates are rubbing back and forth against one another, they'll heat up along the boundary, along the fracture. Warm ice will rise, it's less dense than cold ice, and push up the surface above it into one of these ridges. It sounds a little convoluted, but this way the ridges themselves are part of our manifestation of Europa's tides and actually, therefore, of its ocean. So Europa has this bizarre geology because the ocean is essentially manifest at the surface. The surface is telling us, is behaving strangely because it's being deformed by the tides, in turn because there's an ocean down there. Oh, this is one other. It's the LA model for how Europa's ridges form. We'll get to the spots in just a little while. Really rest stops. Arthur C. Clarke loved this picture, not because of this I did, but because of this. He was fascinated by this one crack that is just perfectly straight and on and on. He thought we should go look for the monoliths. Now, Europa has these other features called bands out there in the ridge plains. This thing's kind of strange. It's kind of sickle-shaped. If you look carefully, it kind of looks like this side might match that side. And actually, look at the older ridges that are cut by this thing. This one looks a lot like that one. That one looks like... So it could be that this just paved over and this runs underneath here. But then here's this one, and here's this one. Here's a real old thing back here, and this thing back here. Well, we use the geologist tool of Photoshop to cut this out and push these sides back together, and they fit perfectly. That's where the band was. So features that were trending different directions fit back together perfectly. This tells us that this thing pulled apart to form the band. Here's a little animation by John Spencer at Southwest Research Institute how this thing may have pulled apart. This probably happened in 10 or tens of millions of years instead of a few seconds, but it gives you an idea. So what's going on there? Did it pull apart atop liquid water, as some people argue, or did it pull apart atop warm, glacial, flowing ice? Remember, ice can flow given enough time. Glaciers flow. So if we see something like this, it doesn't necessarily mean water. It could mean warm ice is lubricating what's below. I've got to say something about the color of Europa, because in a lot of these pictures it looks kind of reddish. And what's this red stuff, people often ask? Well, we don't really know, but we have some ideas. The red stuff might be related to sulfur. Sulfur is kind of orangish, yellowish, red. This is exaggerated color. Europa would look kind of ochre to your eyes, which is kind of the color of sulfur. But from the Galileo infrared instrument, we can get some idea of what's going on in that red stuff. But let's start more simply. Out here in the icy plains, this blue curve is showing what the infrared spectral fingerprint of the light reflected off the surface looks like, and has these very characteristic dips that indicate it's water ice. If you put water ice in a lab, it looks just like that. But if you look at the red stuff, it looks a little different. It has shallower absorption bands and somewhat asymmetrical compared to water ice. Looks somewhat different. And although the fit here at least doesn't look great, if you take either Epsom salt or sulfuric acid hydrate to low temperatures, the fit to this reddish stuff in the infrared is pretty good. Here it's showing it's kind of reasonably good. So it could be that there's Epsom salt, magnesium sulfate hydrate, or battery acid, sulfuric acid, hydrate on the surface of Europa. Well, what's battery acid, if that's what it is, doing on Europa's surface, or for that matter, Epsom salts? Well, Epsom salts could sort of leach out of rock into an ocean. And so that's a reasonable thing to be on Europa's surface if it's oozed up from the ocean. Battery acid's a little odd. Maybe there's a battery acid ocean down there. But what we think is really going on is that the charged particles from Jupiter's magnetosphere are hitting the surface of Europa and creating battery acid, sulfuric acid hydrate. Remember, Europa is immersed in the magnetic field of Jupiter. And again, Io's this litter bug, and it spews out all this stuff. And so there are all these particles that get charged and trapped in Jupiter's magnetic field and are whipping around with this 10-hour rotation period pretty fast and slamming into the satellites, making more stuff that goes into the magnetic field and slams into other satellites or back into Europa. So this may actually make this battery acid on the surface. It can also take things like battery acid and make chains of sulfur, which might explain the red stuff we see. So where does it come from in the first place? Well, maybe it's just SO2 that comes out of Europa, or maybe there's some other chemical that has sulfur in it that gets slammed with charged particles and makes this battery acid. Back to a couple of the geological features. I mentioned Puch earlier. It's about a 20-kilometer impact crater. It doesn't look like typical lunar impact craters, craters on the moon, craters on Mars. It looks much shallower. It's almost like if you touch a cake that's still warm in the oven and it rebounds back after you pull your finger away. That's kind of like what Puch looks like, as if the surface of Europa was warm and then relaxed back up. So it might be that there's warm ice down there. Just the shapes of the craters hint at that. This is Tyre. It doesn't really look like a crater, but it probably is an impact scar. It's probably a place, it's thought to be a place where the impact was large enough that it punched all the way through Europa's ice shell down to liquid water. And a crater couldn't be maintained in liquid. This liquid would quickly rush in and fill the crater, and it would drag the surface along with it into the center and pull the surface in and make these fractures to look like a bullseye. So again, these large impact structures tell us there's probably an ocean down there, and they tell us that, or at least something pretty slushy, and they tell us the thickness, because it had to be a certain size to get through the ice shell down to the ocean, and that thickness of the ice turns out to be about 20 kilometers. So the ice shell seems to be about 20 kilometers thick based on impact craters. We saw the modeled terrain before, the areas where there are spots and splotches on Europa's surface. Here are some more of these pits and spots on Europa's surface. These are each about 10 kilometers across. Here are a couple close up. The light's coming from the right. This is kind of a football-shaped area that's been pushed up somehow. It's elevated compared to the surroundings. And here's a spot that's kind of like one of those hamburger regions where it looks like the surface has been cooked or something has come out onto the surface. So what the heck can make these, especially all kind of the same size and kind of the same spacing? A lot of you look like children of the 60s and 70s like me, so you know lava lamps. So this is the lava lamp model for Europa's for the model terrain. So just like in a lava lamp, blobs of warm wax rise up from where there's a light bulb. They're warm, they rise up in the lava lamp, they cool off, and they fall down again. So this is convection. This goes on inside the Earth, where warm rock rises up from low down in the Earth's mantle toward the top of the Earth's mantle, cools off, and falls down again. That drives plate tectonics on the Earth, probably. Well, Europa may have convection as well within the ice shell. So this is a little cartoon of Europa's ocean. It's ice shell above, maybe about 20 kilometers thick. The tidal heat from the squeezing is melting out the ocean, right? So it's warmest down here. It's the melting temperature of ice. It's 32 degrees Fahrenheit down here or so. But the surface is extremely cold, about minus 350 Fahrenheit. So warm ice is rising up and colder ice is sinking down. This is a fancier simulation illustrating the ocean, which would be down here, the cold surface up here, and these plumes of warm ice rising up. And it would probably take millions to tens of millions of years for these blobs to rise up toward the surface. This is not fast. And it's also kind of tough in these models to figure out how the blobs actually get out, because it's so cold up here and the ice is so stiff that it's hard to get them out of the surface, out of the interior and onto the surface, something we're still trying to understand. This process, this convection, is predicted to kick in when the ice shell is about 20 kilometers thick. So another indication, indirect, of how thick the ice is on Europa. And the last kind of terrain on Europa that I want to show you is the aptly named chaos. Very famous picture. You might not have seen it colorized before, even if you've seen the picture before, colorized by lower resolution color data from the Galileo spacecraft. These city-sized blocks, this is probably 5 kilometers across, what's that, about 3 miles across, size of a small city. These blocks seem to have moved around in something slushy. It sure looks like it's Arctic sea ice or something going on here. So you can see that this used to connect to this, but it's moved around. This one looks like it's been tilted somewhat, and the fin is sort of sticking up. So something happened here to make this chaos terrain. And we still debate exactly what. Did the surface completely melt and liquid water oozed up onto the surface? Or did these blobs of warm ice, these diapirs, this convection process, come up toward the surface and melt out the ice somewhat and then move these blocks around, kind of like stage surfing or something? I'm getting the term wrong again. Like jumping into a mosh pit, and these blocks have been moved around by these diapirs. So these are the two models that we're still debating to understand what formed the chaos terrain on Europa. So I'm generally in the diapir camp, where I think the ice shell is kind of thick and it's mostly this convection that's been going on. But it's also possible that these things, when seen close up, really are icebergs and have moved around right there in liquid water that's now frozen over. Oh, the Titanic is 300 meters for scale, by the way. Let's see if my movie will behave. There it goes. We'll take a look at Connemara chaos, that area you just saw, by zooming in from the global scale all the way down to the smallest scale that we have pictures. So there's Puil, the crater. X marks the spot where down here is Connemara chaos. When we were planning these images from Galileo, a friend of mine called up and said, "Bob, we have to take pictures of the red rabbit." I'm like, "What are you talking about, Jeff?" And he said, "These are the ears," and that was the head of the rabbit. So we went chasing down the rabbit hole somewhat and took images of Connemara chaos close up on that next orbit. It's about 100 kilometers across. Here now you're seeing some of those blocks that have moved around. This bright stuff is ejecta, is material that's been thrown out of Puil crater 1,000 kilometers to the southeast. Zooming in again to those famous pictures, about 50 meters per pixel, showing these blocks that have jostled around relative to one another. Here are fractures size of interstate highways that have cut across the surface. So we can now zoom into some of Galileo's most spectacular and closest up images of 10 meters per pixel, showing these blocks, looking a lot like the cliffs of Monument Valley out in Arizona. Cliff faces and then shallower faces below. These slopes are about 60 degrees. Might make for some fun rock climbing someday. You can see some little craters that are probably debris thrown out of Quill Crater again. Now, as we go out here into that lumpy area, it doesn't look smooth like a skating pond. Oh, here's another one of those blocks. There's an old, battered ridge. Here's that iceberg. Where's the Titanic go? But it looks a little more like this stuff has just kind of disintegrated in place, kind of fallen apart in place, as if it was, again, kind of cooked by heat from below. Heat being warm ice, glacial ice in this case. Or again, perhaps it's melted, and if you melt something out in a vacuum like that, it's going to bubble and froth and be kind of lumpy. So we're still trying to understand which of those models is best. Now, this summarizes, what we think, or at least my picture, of what's going on inside Europa. If you ask another planetary scientist, they might disagree completely. But arguably, we have an ice shell about 20 kilometers thick above an ocean that would be something like 80 kilometers thick, and then the rock down below that. These blobs of warm ice rising up, making these spots and domes. Bands, places where the ice is pulled apart on top of the warmer ice. Chaos areas where tidal heating has just run away and the ice has broken up the surface above it. These multi-ring impact structures having penetrated through that 20 kilometers of ice. Ridges cutting across the surface where fractures have been rubbed back and forth and warmed the ice. So we kind of have a consistent story of what's going on, but this might all be science fiction. We don't really understand, unless we get back there, with instruments that are designed to tell us about Europa's ocean. Galileo wasn't really designed as an ocean detection mission. First, a few more words on why we think Europa is such an important place to go and explore. It seems to have the ingredients for life. What do we mean by that? We mean water probably has 2-3 times as much water as Earth's oceans. Organic molecules, this stuff from which life can be built. So molecules that contain carbon and hydrogen and oxygen and nitrogen. That's kind of a gimme. Most planets have that. It comes in from formation of the world, from comets and asteroids. Water is harder to come by, and hardest to come by of all is chemical energy. So we said Europa probably has tidal heating. It's being squeezed. It's probably hot down there. In the ice, it's warm, maybe down below. Maybe it's hot enough even to melt rock, like Io's rock is melted. But is there chemical energy? And the reason we're getting at this is that most life, if there's life within Europa's ocean, it can't be powered by sunlight. It can't be undergoing photosynthesis. Light only penetrates down so far through ice. But instead, it would need to live off some other kind of chemical reaction. Kind of like life does down at the black smokers on the Earth's ocean floors, places where chemical nutrients are pouring up through these things called black smokers, these chimneys where hot water is seeping through mantle rock, heating up because there's some local hot spot down there in the mantle, and oozing out again rich in nutrients, rich in the kind of nutrients that life can use to power itself. So Europa, if it has a hot mantle, and we don't know, maybe it would have the chemical nutrients for life. But what if it doesn't have a hot mantle? Well, the surface of Europa probably has nutrients that life could live off. There's oxygen on the surface of Europa because charged particles are hitting H2O and forming oxygen and hydrogen. A lot of the hydrogen leaves, oxygen's left behind. So there's probably oxygen, oxidants on the surface of Europa. If they could get into Europa's ocean could have as much oxygen in it as the Earth's oceans do. So we need to understand, can the surface oxygen, oxidants get inside Europa, get into the ocean? So is there the chemical energy for life? Europa has that opportunity, and that's really what makes it different from other worlds that have oceans, well, except ours. Other icy worlds that might have oceans. So Earth has an open ocean. It's the only ocean in our solar system, only H2O ocean, only water ocean that's open to space. Europa has a warm, salty water ocean like Earth's. It's in contact with its rocky mantle like Earth's is. And it's relatively high energy, that is, there's this tidal heating. There's reasons to think that there's heat below and there's geological activity above that could stir nutrients into this ocean. So that's in contrast to the oceans of Ganymede and Callisto, for example. Those worlds are big enough that their ice is not just above, but below the ocean. So what's that about? Not just big enough, but they have enough H2O. They have so much H2O that down below the ocean, that water is compressed into another form of ice, a high-density form of ice. So the oceans are sandwiched between ice layers. Those aren't great places energetically for life. There may be an ocean within Titan at Saturn, moon of Saturn. You're probably familiar with Titan's open seas that are probably methane. So Earth's not the only one with open seas, but the only one with H2O seas. Titan probably has methane and ethane lakes and seas on its surface. And it probably has an ocean below the surface as well, an ocean that probably consists of not just water, but ammonia and water. I mean, if Callisto has an ocean, Titan's got to have an ocean. It's about the same size. Callisto's pretty dead. To make oceans in Callisto and Titan and in smaller icy satellites probably takes ammonia. Ammonia lowers the melting temperature by a lot, by 100 degrees Kelvin. And so it's possible that lots of the middle-sized icy worlds, moons, and also dwarf planets, including Pluto and Eris. Here's Triton at Neptune. They may have oceans within as well, but only if there's lots of ammonia. That means there'll be cold oceans, and they'll be rich in ammonia, and that might not be a great place for life either. Now there's also little Enceladus at Saturn. It has these plumes of water vapor coming off of its south pole. We now know, recent discoveries from Cassini. It's thought it might have an ocean within, or maybe just a south polar sea beneath this area that's especially active. We don't really know. We're still trying to understand, is it a hot, warm, salty ocean, or is it a cold, ammonia water-rich ocean? So of these potentially 13 oceans in our solar system, other than Earth, Europa seems the most promising to go explore, and potentially the most accessible, the one that's communicating with the surface. And that's why we've been working hard, the science community and JPL have been working hard to try to get a mission to go back to Europa, to orbit Europa. Because from orbit, the tides could be directly measured. We don't have to infer the tides. We could measure them and say, yes, they're 28 meters on the course of a day. And that would tell us something about the properties of the ice, like its thickness, or some indication of its thickness, even the thickness of the ocean. We could measure the magnetic field over long time scales and get at the thickness and saltiness of the ocean beneath. We could map out all of the surface. You know, Galileo was quite handicapped. Next door you can see the mock-up of the broken antenna. It was transmitting data through a backup antenna the size of a coffee can lid at 40 bits per second. So we really don't have a lot of those great images that I was showing. We need to understand Europa globally. This spacecraft would probably carry a radar antenna. And radar, like the Mars Reconnaissance Orbiter spacecraft is doing now at Mars, radar can penetrate through ice and reflect off liquid water that exists below the surface. So that radar might be able to penetrate all the way down to the ocean and tell us how deep it is. And it could find water within the ice shell related to these blobs of warm ice, for example. We could do a better job at composition. We could really understand Europa as a world and go searching for those ingredients for life. It'll be a while probably before we can get a lander to Europa. If there is an ocean there, if we know that from an orbiter for sure, if we're able to find thin spots in the ice, we might send a lander down, scoop up some of that red stuff, and really get at what is the chemistry of this stuff. And for that matter, at that point, we might search for some evidence of life itself. And then, probably not in our lifetimes, but maybe, someday we'll land on the surface of Europa and melt our way through down to the ocean below, like depicted in this illustration, although it's probably got 80 kilometers to go between the ice and these hydrothermal vents depicted down here. So Europa is a world that once, long ago, 400 years ago, was one of the four worlds seen by Galileo, which helped change our perception of how humans fit in to the cosmos, how we fit into the universe. And it's just great that one of those worlds, Europa, may be the place that allows humans to do this again, to find out if there's life on another world, and if so, could really once again change our sense of place in the cosmos. Thank you very much. So hopefully it's time for some questions.
Yeah, I remember the older models show the rock and ice of most of these worlds more mixed. Does the separation of the rock and ice indicate that there was a massive early volcanic epoch? And if there's sulfur mixed throughout the interior, if there's sulfur mixed throughout Europa, does that indicate maybe a volcanic epoch like the one on Io?
Okay. So let me take those couple of questions. I'll repeat them in case it can't be heard. So it used to be that models of the satellites depicted the satellites as kind of uniform mixtures of rock and ice. And that's because it wasn't clear that they could be heated enough for that differentiation to occur, the separation of the rock from the ice. And it seems not only has rock separated from the ice, but metal has as well. These things, were mighty warm early on. I mean, Ganymede has a magnetic field. So its interior must be still hot today. It's probably cooling off today from a warm episode. So yes, that tells us that these worlds got very warm early in their histories and have caused revision of ideas of how satellites form. A weird thing is that we don't know if Callisto is differentiated or not. And to keep Callisto from differentiating, but allow Ganymede and Europa to differentiate, that's kind of hard to do. You have to maybe make the Callisto more slowly. And then you asked about sulfur and its implications. We really need to understand, first, is that sulfur? And then, what does it come from? Is it SO2, sulfur dioxide, that it comes from, or is it something else? Is it a battery acid ocean in there? So really, to understand the implications, we need to get at really what is the chemistry in there. But it has been suggested that maybe it could mean it's kind of Io-like down below and the mantle is really hot. but we don't know for sure. Questions? Yeah.
If there was any life ever in the ocean at the bottom, and that there was, so therefore there'd be organic compounds in the water, and maybe that might have gotten to the surface through some of the cycling and mixing, is there any hope that those organic compounds would survive on the surface, or would they have been just disassociated by the cosmic?
Okay, so the question is wouldn't these charged particles destroy organics on the surface? Actually, the answer is yes. They would destroy organics on the surface. And so unless there's stuff that's come up very recently, like tens of years, we might not be able to find organics on the surface directly. Now, it might be that there were nice organic molecules that are being broken apart, and we're not sure how much radiation it takes to really destroy it to the point we can't even recognize organic molecules. One idea is that the Europa Explorer spacecraft and orbiting the satellite could pick up particles that are sputtered, as it's called, that are shot off the surface by these charged particles, and maybe pick up organic materials. But it also means that if a lander goes to Europa someday, it'll probably have to dig below that radiation processed layer to try to get at fresh stuff. So there's a chance we'd find fresh stuff from orbit, and we'll look from an orbiter, but it's more likely that it's been processed by the radiation somewhat and destroyed somewhat. But it's not out of the question to find organics there. Yeah, in the back.
You were comparing the basis of Europa's oceans to hydrothermal vents on Earth's surface, and I wondered how would the temperature and pressure and the variations in those compare to what we find on the base of ocean?
So as the temperature and pressure compare, especially as related to the hydrothermal vents, the pressure at Europa's ocean, if it's really under, if the ocean plus ice is about 100 kilometers thick, because the gravity is less, it's about a sixth or seventh of Earth's gravity. It's about the size of Earth's moon, so similar gravity to Earth's moon. And so the pressure down at the bottom of the ocean is like the pressure at the deepest points in Earth's ocean. So if you go down to the bottom of the Marianas Trench on Earth, the pressure is similar. So there aren't hydrothermal vents down at the Marianas Trench. Where there are hydrothermal vents on Earth, it's all lesser pressure by, I don't know, about half or so. And so actually there are some experiments starting up here at JPL to say, can we take organisms that we find in the Marianas Trench on Earth, put them in a chamber that's Europa pressure, and see if they survive? See if they survive under similar temperature, pressure, and chemical conditions as on Europa. Temperature isn't really a problem. It's a similar temperature. It's kind of the melting temperature of water. Yeah. So really the pressure and the chemistry are the big issues. Yeah.
What would be the one bit of evidence that would nail it down as an ocean? What would you say, there's an ocean?
What would really nail it down as an ocean? The basic simple experiment to do is the amount of tidal flexing. If it's 30 meters, there's an ocean. If it's 1 meter, there's no ocean. And if it's something in between, it probably means there's an ocean but a thick ice shell on top. So just by measuring the amount of tidal flexing, by using gravity from an orbiting spacecraft and altimetry from an orbiting spacecraft, measuring how much it's flexing, we would know for sure that there's an ocean.
How long do you think it would take in orbit to gain that data?
How long in orbit to do that? When I talk to the geophysicists who think about these things for Mars, and they say about 2 weeks, all you need. Really just orbit for a couple of weeks. We might know the answer in days. But to do it right, probably a couple of weeks. And this Europa Explorer would orbit for 6 months to a year. So we really get to the higher level of, is the gravity telling us that there are big islands down there on the floor of the mantle? I mean, we might get to that level with the gravity data in that amount of time.
In that salty ocean, would you expect it to be mainly sodium chloride salt like ours, or would you expect to find some other kinds of salt?
Well, so what kinds of salt in the salty ocean? Again, I'm not a geochemist, but from what I understand of it, actually we should ask Steve this. things like magnesium sulfate are expected. If you take a meteorite, at least I can understand this aspect. Take a meteorite and cook it, and you get things like magnesium sulfate coming out of it. And so that's thought to be something that should be there, and the spectrum of it matches reasonably. Sodium chloride, are we expecting stable salt in Europa's ocean? I'm pointing this to Steve, who studies the chemistry of
from what I understand, magnesium sulfate should be present on Earth, but it's buried largely in the mantle through hydrothermalism and through plate subduction.
Oh, so we should see magnesium sulfate on the Earth, and we don't because it's buried down by these pesky plate tectonic processes on Earth. So it's reasonable.
And say, well, that could mean there's not a whole lot of hydrothermal activity on Europa because there's magnesium sulfate. But what's meant by not a whole lot is hard to say.
Other questions? One more.
What would you guess the pH of the water would be?
Oh boy. Almost anything. And when I talk to the people who are really trying to understand if there could be life there, they want to know what the pH is. That's a real fundamental issue for astrobiology. And we don't know. Is it a battery acid ocean, right? Or is it an alkaline ocean? So really we don't know. But if we could measure it, we could say something important about the nature of the ocean. And well, I want to say it's habitability, but life is pretty adaptable to.
So if you talk about your vent theories, where at the vents it's relatively acidic, and then the question would be, there's always this gradient, this pH gradient around these thermal vents on the Earth's ocean floor. The question would be, would you get that same kind of gradient? And so would there be a little narrow gap in which the environment would be ideal to produce a living organism?
Again, life is so resilient, and when we look at these images and when we think about Europa's processes, the first thing goes into our heads is what we know, right? And we think black smokers, and maybe that's going on. But if you ask someone, before we knew about black smokers in the late 70s, they'd say, no way. Or before the Voyager spacecraft saw that these moons had active geology. So these moons and life on them, I think, could adapt in ways that we haven't even thought of yet. Okay, I'll stop there. Thank you all for coming. Please feel free to come up if you have additional questions.